So in this lecture, we're going to be going into more depth about electron beams and electron interactions. We're going to talk about charged particles, explanation of continuous slowing down approximation, which is what electrons do. A little bit on how ionization becomes dose and high and low linear energy transfer and radiobiological effectiveness. So just a reminder, charged particles are electrons, positrons, protons, things that have a positive or a negative charge. They have a magnetic dipole and they have mass. Those are all what we're talking about when we're talking about charged particles. And two things can happen when a charged particle interacts with matter. So when we take an electron beam and we throw it at one of our patients, those electrons can come in and some of them will ionize. They'll do atomic interactions. The energy will get transferred to an electron in that atom and create ionization, which is dose. The other thing that can happen is that they can make X-rays. They undergo nuclear interactions, produce some bremsstrahlung, which is braking energy. When this electron curves around this nucleus, it's accelerating, slingshotting off of that nucleus, and that slingshot creates an X-ray. For the most part in this lecture, we're talking about ionization and what electron beams do. So here's a super complex equation that you don't need to know. The important part of this equation is that the energy loss of a charged particle using the continuous slowing down approximation is a function of the velocity of that charged particle. So when we accelerate electrons, they come up towards the speed of light. Their energy increases, but their velocity basically plateaus right up at the speed of light. They're always just under the speed of light. And in this graph, you can see this graph is showing us ionization as a function of particle energy for different materials. And you can see when you're up here at high energies that our electron beams are at, they're all very close. Water, aluminum, copper, lead, it's all kind of the same. And in this one, the density has been removed from it. So this is independent of density. The energy loss is very similar. As the kinetic energy increases, as the T, as we call it, increases, protons and electrons' velocity come up towards the speed of light. Nothing can go faster than the speed of light. And the ionization plateaus because the velocity is basically equal to the speed of light. And then the ionization increases as the velocity decreases. So when a charged particle comes in, it's going to be up in this region right here where we are. Let me make sure my laser pointer is on. Here's I don't think that's the laser pointer. Laser pointer, there we go. Our charged particle electron beams are up in this relativistic region, and their energy loss is pretty constant. As that electron beam passes into our patient, it's going to start to slow down, it's going to start to lose energy, and then the energy loss skyrockets. So it comes in, it's losing energy very slowly, and then as soon as it starts to slow down a little bit, come down off the speed of light, the energy loss goes really high. And when we put this graph along with the graph of a Bragg peak curve, you can kind of see what's happening. When this is an alpha particle going at 7.7 or has an energy of 7.7 megaelectron volts. In this region, it's in the relativistic region, its energy loss is kind of constant. I mean, it is losing more energy and accumulating, slowing down and increasing its ionization as it gets deeper inside this patient. This is in the relativistic region. But then later, as the velocity comes down and its energy loss skyrockets, you get this Bragg peak out of it. That's effectively what's happening, and this is what creates the Bragg peak. Particles that come in, they'll start losing energy, it's kind of constant, but then as they get into this lower energy area, their energy loss skyrockets, you get this big burst of energy lost right at the end, and then it plummets. So that's how protons and electrons and other charged particles lose their energy as they enter into a patient. Just to reiterate the path length of charged particles of an electron versus other particles. So in our department, we use electron beams. This electron right here is going to ping off of all kinds of different things inside of our patient, all kinds of molecules. It's going to take this torturous path before it finally stops. And you're going to get some sort of depth dose like this. So it's going to deposit depth inside the patient. That's different than here's like an extreme example, an alpha particle, which is heavy and has a charge of +2. And this is basically going to plow into our patient like a dump truck. So here it is plowing into our patient like a dump truck. It's going to be losing energy kind of consistently, and then all of a sudden it's going to spike its dose and go down. So that's basically one of the differences between protons and electrons. Proton beams tend to come in, plow into our patients, and then do a nice quick Bragg peak, whereas electrons are a little bit different. They scatter so much that they don't have a distinct Bragg peak. So direct ionization, this is what happens when charged particles interact with matter. Charged particle delivers their energy directly to the matter through a series of many Coulomb interactions along the way. So in practical terms, that particle is charged, and as it enters into the body and it's passing all of those different atoms and molecules and nuclei and things like that, because it's electrostatic, it's always interacting with it, right? It's always trying to cling to the nuclei, it's always bouncing off of them, it's always orbiting around them and doing things like that. And so it's undergoing many electrostatic interactions or Coulomb interactions along the particle's path. For X-ray beams or neutron beams, we say that they do indirect ionization. So an X-ray will pass through a patient completely unnoticed until it does its first interaction. And then once it does that first interaction, it'll release some electrons, which then go on to do direct ionization. So in this way, we say that X-rays and neutrons are doing indirect ionization. They're not doing it directly. It's the result of their first X-ray interaction or neutron interaction that creates the ionization by subsequent charged particles that they release. Here's a diagram depicting the X-ray mode and electron mode of the Linac. In electron mode, the X-ray target is retracted. The primary electron beam passes through the primary collimator down to the part of the machine that's called the carousel. The carousel has a scattering foil on top of it. It will scatter these electrons through the monitor unit chamber and the jaws and down towards the cone. And the way I've diagrammed it here, all of the electrons following these red paths are stopped by the cone or the jaws or something like that. And all the electrons along the green path are able to come all the way down through the cone and make it to the surface of our patient. And you can see, because of the position of the scattering foil and the relatively large scattering spot of the electron foil, the scattering foil, we need this cone to help contain all the electrons, or else the electrons would leak out and deliver dose to parts of our patient far away. So it may be, let's say, like this particular ray right here. If it didn't have this thick cone, basically blocking this beam from getting away from what we want to treat, this electron might come down and treat somewhere else inside the patient. So it's different than X-rays. Remember, X-rays are going to go in a straight line forever until they interact with something, whereas electrons can do things like bounce off of jaws, bounce off of cones, bounce off of cutouts, and then this is why we need to contain them within the cone. This is what a scattering foil looks like from a Varian Linac. I call this like a two-stage scattering foil. The first is for the main beam, so it has this scattering point up here, diagrammed here. It gets this initial beam scattering, and then below it you have on the second stage this cone of what to me appears to be aluminum, and it creates like a larger focal spot size than the X-ray, and also that scattering foil is very much lower inside the Linac than the X-ray target. Each energy has its specific scattering foil, so every single energy in your Linac has its own, and it's designed to scatter electrons and not produce Bremsstrahlung X-rays. So it's thin and it's made out of low Z materials. Low Z materials, remember, are poor at producing X-rays. They are less efficient at producing X-rays with electron beams than high Z materials. So this is appears to me made out of steel. This first scattering foil seems to be some sort of stainless steel, and then this scattering cone at the bottom is made out of aluminum, as far as I can tell. Some other considerations. Electrons are collimated by an applicator. It has a cone and a cutout or insert. This is looking up through the bottom. The cutout is placed at 95 centimeters. And you can ask the question, we could place this cutout anywhere we wanted, right? We could design the Linac to have the cutout up here instead of down here. So why is the cutout so low and placed so close to the patient's skin surface? Well, the electrons have a large source spot size and a lot of geometric spread. So it makes putting the cutout as close to the patient's body surface as possible advantageous. In fact, in radiotherapy, anytime you have a lot of geometric spread of the beam, whether it be X-rays or electrons, it's always good to put a collimator closer to the surface. And this is also why when we do patient setups, we always say that 100 SSD is the optimal patient setup. Treating the same beam with the adjusted field size at 110 isn't as good, because you're going to get some, within just that 10 extra centimeters that you've added, you'll get a little more geometric spread, and that electron beam edge isn't as sharp as it could be. So electron beams have certain characteristics. The shape of the electron percent depth dose curve makes it ideal for many single beam treatments. So here's a diagram of what the relative depth dose is, percent depth dose is of this particular electron beam. You can see here that they do, this one's showing maybe about 80% dose at the surface. It comes up to a maximal dose, and then it drops off quickly. It has uniform dose with fairly rapid fall off, especially energies that are like 6 to 15 MeV. And unlike photons, skin sparing is lost as the energy decreases. So for high energy electrons, they lose energy at a rate of about 2 MeV per centimeter in water. This is a really important concept to learn. Go ahead and memorize it. For every centimeter of water, your electron beam is going to lose 10 MeV per centimeter as it penetrates the patient. So the depth of penetration is 0.05 centimeters per MeV. Or you could say beam energy divided by 2, right? So just energy divided by 2. If you have a 6 MeV beam, 6 divided by 2 is 3. The beam is going to penetrate about 3 centimeters. 9 penetrates 4.5. 16 divided by 2 is 8, so 16 MeV beam penetrates about 8 centimeters. This is like a rule of thumb that everybody uses. And we're going to do some calculations with this. And the position of this, so you can see in this diagram here, we have this curve drawn this way. It has this quickly dropping slope. We draw this line to it, and we have this position RP. And RP is the practical range of the electron beam, and we call that basically energy divided by 2. So here's a whole bunch of different things about an electron beam. And you should look at this slide and try to memorize as much of this as you can. This green line here is the dose deposition of the electron beam as it penetrates into the patient's body. This is depth. You can imagine if you're hitting my head with an electron beam, it's going to deposit about 90% of the dose at the surface. The dose is going to increase in my scalp till it hits about Dmax of the beam. Dmax is the depth of maximum dose of that beam. There's a concept called R90, which is the range for 90% of the dose. So the depth that 90% isodose line occurs at. R90 is about energy, the beam energy divided by 4. Another one, this is like the typical range used for prescription depth. So like when a physician knows how deep they want the beam to penetrate and they know what depth they want, they can effectively multiply that by 4 and figure out what electron beam energy to use. Another concept is called R80. It's when you have 80%, the depth that 80% of the dose occurs at in the patient. R80, it's the accelerating potential, the beam energy divided by 3. R50, this is an important concept for beam calibration. It defines the depth of 50% dose for calibration. Down here you have RP, practical range. It's basically the beam energy divided by 2. It's the range kind of extrapolated for this X-ray beam coming out this way. And here we have the Bremsstrahlung X-ray. All of these, despite the fact that these scattering foils are designed to scatter electrons and not make X-rays, as you increase the beam energy, you need a bigger scattering foil because those are faster moving electrons, or I should say more energetic electrons, right? I just said earlier they don't move faster. And there will be some X-ray production in the scattering foil, so you have a little bit of X-ray dose. It's basically like a little mini X-ray beam penetrating into our patient. So look at this diagram. If you have any questions about it, just let me know. I will answer them. Here's a comparison of the rules of thumb versus reality. So for R90, we have, these are all the beams that we use in our clinic, 6, 9, 12, 16. We don't use 20 anymore. We turned it off. And in this column here, it's just the simple math. It's the energy divided by 4. And then in this column, I have what our beams actually do. So I actually took the real beam data that physics collects as part of their commissioning, pulled that number out. And you can see that these things don't match up too well for R90. At low energies, 1.5 centimeters deep for E divided by 4 compared to 1.8 centimeters deep for R90. And you can see as the energy increases, 2.3 versus 2.8, that's 5 millimeters off in prescription depth. That we would call that a lot these days in radiotherapy. This is at 12 MeV, it's 3.0 versus 3.9, almost a whole centimeter difference. When we get to 16, we're over a centimeter, and at 20, we're right around a centimeter. For the 80%, this fits a little better, R80. 2 versus 1.9, 3 versus 3.1, all the way up. It's a little more stable calculation. And then the practical range here, so this is one that we use quite a bit. Energy divided by 2 for 6, 9, 12, 16, and 20 MeV. And you can see it actually fits pretty good. 3.2 centimeters for 6, 4.8, so that's 3 millimeters off, 4 millimeters off here. And then when we get to 16, we're 3 and 4 millimeters off. So the practical range is pretty reliable metric to calculate. For electron beam calibration, the vast majority of clinics calibrate to 1 centigrade per monitor unit at Dmax for each X-ray energy using the 15 by 15 cone with the SSD set to 100 centimeters to the surface of a water tank. And then the output reference depth is Dmax of the beam. So every single beam in our department, 1 centigrade per monitor unit at Dmax, 15 by 15 cone, 100 SSD to the water surface, Dmax. That's the calibration condition. So let's do a simple example, practical range application lead shield for an electron beam. So let's say like we want to shield the skin surface from an electron beam treatment. Maybe there's something sensitive there that the physician doesn't want to treat. We're going to use a 9 MeV electron beam. We're going to say that this beam loses 2 MeV per centimeter in water. That's our rule of thumb. We use it all the time. So let's say like we're going to use bolus, right? We'll say, well, we have a lot of bolus on hand. We're just going to bolus this patient until the beam stops. So if we take 9 MeV, we're assuming bolus is just like water. So we divide by 2 MeV per centimeter. We get out that we have to use 4.5 centimeters of bolus to stop this electron beam. Can you imagine like stacking almost 5 centimeters of bolus on top of our patient? Wouldn't be very practical. So let's use lead instead. Lead has a density of 11.34 grams per centimeter squared. And I mentioned earlier that for a lot of these beams, when they're at high energy, it doesn't really matter what material they're made out of. And because 11.34 is a difficult number to work with, we're going to round down. So let's just round down to 10 grams per centimeter cubed of lead. And when we do this, we're going to be overestimating the amount of lead we need to shield our 9 MeV beam. And let's assume lead is the exact same thing as water, just more dense. So if we have this calculation, we're going to take 20 MeV per centimeter. So to get that, I took 10 and multiplied it by 2. So lead will be pulling 20 MeV per centimeter of the beam out in lead. So if I do 9 MeV divided by 20 MeV per centimeter lead, then in that situation I need 0.45 centimeters of lead to shield this. So this is a 4.5 millimeter thick shield of lead to shield a 9 MeV electron beam. So that's much more reasonable. So here's another thing to consider when doing electron shielding. These electrons can do two things, right? Certainly they can stop in the shield, that's what we want them to do, but they can also scatter outside the shield. This can have an effect. It can reduce and in some cases increase the dose under the shield or directly adjacent to it. And so in this diagram right here, I have an electron beam with an energy of 25 MeV, and this lead shield right here is too thin. I'm just going to tell you, someone made this shield. It's not thick enough to shield this beam. And you can see, like, when the electron beam passes next to this lead shield, nothing happens. This beam penetrates the patient, it's just fine. But some of these electrons that hit this too thin shield will basically scatter out of the shield and won't get stopped in it. They'll scatter outside and they'll contribute dose off to the side. So they may reduce the dose a little bit under the shield, increase the dose adjacent to it. So this is what this looks like. So you can get significant dose increase at the edge of the shield. Now, clinically, our shields are always thick enough. We always make sure they're thick enough to use. But what can happen is if you have a shield coming down and it hits just on the edge, so maybe we plan to make the shield 4.5 millimeters thick. It is 4.5 millimeters thick. But some of that electron beam may just be catching just a part of the shield. You can get some of this dose in here catching the shield and scattering back out, and you can get these weird things happening. So with this shield that's too thin, you can see Dmax of this beam got pulled up towards the surface. This is depth in centimeter right here. So this is 0, maybe 1.7 centimeters deep for this 25 MeV beam. So Dmax got pulled up right underneath this lead shield. And then you get these enormous dose increases. So you can get 120 dose. I think this tiny line in here was 150% dose, 110. Here's the 100 dose line snaking through the patient. And you can get these weird little dose increases right next to the patient. So, the lesson here is that make sure the shield is thick enough. You want those electrons to stop in that lead shield and not go through it. You want to reduce the overlap of the electron beam with the shield if at all possible. I know a lot of times in my clinic we use lead shields as backup. So if we're planning a treatment on the patient's forehead right here and we want to make sure the eye doesn't get any dose out of a safety shield, we make sure that the light field is outside the lead shield and not inside it. So make sure you don't overlap the E-beam with the shield if at all possible. And a lot of times what we do is we add lower Z backing to the shield. So here's some eye shields that we made, and they've been wrapped in thermoplastic. The idea being that if there is a tiny dose increase, that dose increase is inside the thermoplastic and not inside the patient's eyes. And it also adds a little bit extra material for the electron to stop in. And it also gaps the shield off the patient's skin surface, which can be helpful. Here's another application, tungsten eye shields. So tungsten eye shields are used with 6 MeV electron beams to the lower lid. Here's an example that we're going to run through. Tungsten has a really nice density. It's 19.25 grams per centimeter cubed. It's really high density. And we can have two thicknesses of our eye shields. We have 2 millimeter and 3 millimeter thick tungsten eye shields. So if we just run through the math, and once again we're pretending that tungsten is exactly like water in terms of its reduction of beam energy per unit centimeter. So we have 6 MeV divided by 2 MeV per centimeter. That's our rule of thumb. Taking into account tungsten, 19.25 grams per centimeter cubed, and then converting from centimeters to millimeters, we find that if we want to shield a 6 MeV beam with tungsten, we need to use a 1.5 millimeter thick tungsten shield to stop a 6 MeV electron beam. So The tungsten shield that's 2 millimeters thick has an extra 0.05 millimeter of tungsten on it, which should completely shield that. You may also know that these tungsten shields have an aluminum backing, so I kind of diagrammed it here in blue, and you can just see it in this here. The aluminum backing is designed to absorb backscatter to the inner eyelid. So what can happen is an electron beam can come down, hit this tungsten, and bounce backwards, and then you'll inadvertently be increasing the dose to the eyelid. So you maybe want to treat the eyelid to prescription dose, but you don't want to go over. So we put this aluminum absorbing material on the back of it. And it's important to remember that you cannot use the 6 MeV shield with the 9 MeV beams. It's just not thick enough. You have to use the 3 millimeter shields with the correct electron energy and the 2 millimeters with the correct electron energy. That's why we have two different ones. This kind of is an extreme example of what would happen if you were to use the wrong shield. So in this example, we have a 6 MeV electron beam. They have these lead eye shields, orthovoltage shields used for electrons. These were used for X-ray treatments to the face and the eyelid and things like that, but they're made out of lead. They're probably good for that ortho machine, but they're just not thick enough for a 6 MeV electron beam. You have to use tungsten. And in this diagram, you can see the tungsten shield has really reduced the electron dose underneath the tungsten beam. Here's the 3% isodose line. Whereas the lead shield has not reduced it, maybe only taken it down by half to the lens of the eye underneath the lead shield. So you just got to make sure the lesson, use the correct shield for the correct beam. And also, these are not suitable for megavoltage shielding at all. The tungsten shield simply is not thick enough to reduce our X-ray treatments by enough at all. We basically don't ever use tungsten eye shields with megavoltage X-ray beams ever. So a little audience participation time. Why do we use lead and not tungsten in the clinic to make eye shields? If the density of lead is 11.34 grams per centimeter cube and tungsten is all the way up at 19.25, it's a lot more dense. We could use much thinner shields. The patients might like it better. Why don't we do that? And the simple answer is lead's easy to work with in the clinic. So if I think this was like a shield that was made to go underneath someone's eyelid on their cheek or something like that, the therapist can cut out a paper template out something during the sim in the treatment room. And you can make a template, and then it's easy to transfer this to some lead sheet, cut it out with a pair of scissors, and then wrap it in tape to keep the lead off the patient's skin surface. So the short answer is it's easy to make one out of lead. Even this week, I was able to take some office scissors and cut 3.5 millimeter lead sheet to make a patient shield. So it's easy to work with. That's the answer.